Welcome to the pre-calculus video on algebraic notation and rational exponents. Due to the length of the content in this video, I only am going to focus on algebraic notation. I will do the rational exponents in a follow-up video. We'll start the video with talking about algebraic notation, and most specifically we'll be expressing our solutions often in set builder or interval notation. When we move on into calculus, interval notation is perhaps the most common method of expressing solutions. So let's talk about algebraic notation. Okay, when it comes to talking about sets of numbers or solutions that cover a range of numbers, one tool that we might use is set notation. And set notation is usually defined by using braces and then listing the values in the set. So for example, if we wanted to talk about the set of natural numbers, we would say the set includes 1, 2, 3, 4, and we can't list all of them, so common practice would then be to, once you've established the pattern, put in the ellipse and then close the set. Something that is worth noting about the set of natural numbers is even though there are an infinite number of numbers in the set, we can still call it a countable infinity. In other words, we're able to count all of them up. There's this one, and then this one, and this one, and this one, on down the line. So it's a countable set, countably infinite. Moving on to the integers. Now the integers is another set that we can define with braces. And the set of integers is 0, 1, -1, 2, -2, and it keeps going forever in both directions. So we could write it like that. Now the interesting thing here is it's a little bit harder to count because we have ellipses on both sides. So you could say this is non-countable. However, there's nothing that says that the set needs to be written in ascending order. So a tricky person might rearrange the set to be 0, 1, -1, 2, -2, 3, -3, etc. The pattern's established, and suddenly we've made our set countable. Now this feature of countability of the set we don't get into much in pre-calculus, but it is an interesting thing to explore on the side. The rational numbers is where we start to get into some pretty interesting problems because you can't list out every possible rational number. And remember, rational is based in the word ratio, so it's going to be the ratio of one integer to another. So then what we can do is we can write out this set. We'll say Q is equal to the set of numbers P over Q, provided that P is an element of the integer set and Q is an element of the integer set. And if we're being very tricky, Q is not allowed to be a 0 because you can't have zeros in the denominator. So, if we do that, then we cover all rational numbers. Proving whether this is countable or not is actually a pretty interesting side project that we're not going to get into, but this is not countable. There's an infinite number of values in that set. Not only that, it's a infinite that's bigger than this infinity. So yes, there are different sized infinities. The irrational numbers would be the list of numbers which are not rational. So we could actually make this set very quickly by saying the set of all values k such that k is not an element of the rational numbers. Then the real numbers is basically the two combined, rational and irrational numbers. So we could denote that as the set of rational numbers in union with the set of irrational numbers. And that U symbol there is a joining symbol, which means let's join these two sets together. And real quick, example of an irrational number I should have covered earlier would be like pi, or we'll use the value e a lot in pre-calculus, maybe the square root of 2. Basically, it's a non-repeating, non-terminating decimal. And then a real number is a terminating or repeating decimal. So the last set that we have here is the complex numbers. And complex numbers we're going to explore later on in the year. Most of us were first exposed to it by talking about the square root of -1 is equal to I. And I is the imaginary number. Well, a complex number is the combination of a imaginary number and a real number. So the way that's typically written is some value a plus b times I, where a and b are both real numbers. And if we wanted to, we could add in I is defined as the square root of -1. So these are various ways that we talk about sets using these braces, and we'll explore sets a little bit more in some examples further down here. So one common setup is that we'll see things listed in set notation and we need to move it to interval notation. For example, we'll see something like, we want the set of all x's such that x is less than 3. And we can write that, you could write, all right, well, this is 3, 2, 1, 0, -1, and it keeps going. Oh, I forgot about, 2/3 and -1/7. And this gets a little bit cumbersome to list them all out. This set notation here is probably the cleanest way that you could list them all out, but we want to be able to express it in interval notation. And so that's the second example we're going to take a look at, expressing this as interval notation. And you can think about this on a number line. We're talking about 1, 2, 3. We're talking about all the values left of 3 on the number line, not including 3. So let's look at example 2, and we'll move through this pretty quickly. Okay, they are asking for a number line graph and the answer written in interval notation. So in this case, what we have is the values from 4 to 9, and we are not including 4, and we are including 9. And we want all the values in between. So there's our number line graph. It's not necessary to write in these midway points, but if you wanted to, you could. I think just capturing the end values is good enough. It should also be noted that when your end value is not included, this is just less than, we do an open circle, and when it is included, we do a closed circle. And as far as translating this into interval notation, our lowest possible value is 4, our highest possible value is 9, and we always go from lowest to highest. And then to express whether we include it or not, to not include is a soft parentheses, and to include is a hard bracket. So this is called interval notation. And most often, this is the way that I like to see answers expressed. And a lot of what we do on forward in calculus, interval notation is the most frequently used form for expressing a set of numbers. So moving over to part B, we first draw our number line. So we have values 4 and 9, so I'll just drop those on there, 4 and 9. And in this case, we want values less than 4. And so we go to the left, we don't include 4, and we want greater than or equal to 9, so we do include 9 and go to the right. So in this case, our set is split into two different pieces, so we're going to need two different sets using our interval notation. So in our first interval, our lowest value is negative infinity, and our highest value is 4. We do not include the 4, so it gets a soft parenthesis. And infinity, since it's not a real number, we can't technically grab it, so infinity will always have the soft parentheses. On the right, our lowest value is 9, and our highest value is positive infinity. We do include the 9, so we use a hard bracket, and again, infinity always gets soft parentheses. So there's our two sets in interval notation, and since we're talking about the two sets, we want to include the or statement. So this is, you can consider this a disjoint set because they're disconnected, as opposed to this, which is a single set. All right, let's move on to example 3. Okay, we need to express in both set and interval notation. So right away, I'm going to talk about set notation. And in this case, we're talking about temperatures, so let's just call our variable T. And we want the temperatures for which water is solid. And for those who don't know, scientifically, water is solid when the temperature is less than 32 degrees Fahrenheit. So we want all T's such that, and this vertical bar means such that, T is less than 32. Some could argue at 32 it freezes, so let's include that value at 32. So there's our set. If we were to express that in interval notation, our lowest value is negative infinity, and our highest value is 32. And we include 32, and we can't include infinity. Though I think technically, and this is a little bit outside my domain, the lowest possible temperature, absolute zero, is somewhere around minus 273 Fahrenheit. I could be wrong there, don't quote me on it, but from a mathematical standpoint, this set translates to that interval notation. And this infinity versus 273 is a scientific piece. I, of course, won't give you anything like that, that you have to know that. The idea is the important piece. Then we know that water is a liquid from 32 degrees. From 32 degrees all the way up to a boiling point of 212, at which point it turns to gas. And deciding whether or not to include the 32, I included it in part A, so I'm not going to include it in part B. That value at 32, where water is both solid and liquid, is a little fuzzy with the science math overlap. But let's move forward. 212, I'll just not include that and show you what the braces or the set looks like. All temperatures such that 32 is less than T is less than 212. So there you go. There's your set notation and interval notation. And then finally we want to move on to the gaseous state. And the gaseous state would be when water temperature exceeds 212, so when T is greater than 212. And in this case, I will include the 212 since it was not included in part B. So here we go. Moving to interval notation, we're going from including 212 on up to infinity. So very, 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 very hot. Okay, one of the key things to understand about interval notation and set notation, or sometimes set builder notation, is each one of them is kind of beneficial for different types of answers. For example, if the solution were all numbers from, we'll say 3 to 100, then it might be good to use the interval notation. If your answer was just 5, well, it's kind of hard to write 5 as an interval. So instead we use a set notation as opposed to the interval notation. And developing a intuitive understanding of when to use which is of benefit, but more often than not, I will tell you express your answer in interval notation. Sometimes you'll see me write answers out in set notation or give you information in set notation. So in example 4, we're going to talk about trying to see which of these two notations is better. For what types of numbers can we use interval notation or set notation? Write a notation to represent all the integers greater than 4 but less than or equal to 9. Well, the mere fact that it says integers kind of makes me want to actually list them out, even if it might take a while. So let's list them out. All integers greater than 4 but less than or equal to 9. So I list all of them out like this. It's a set. I double check my work and I see that it says greater than 4. So technically we don't include 4. So that's not in the set. And then we check on the other end, less than or equal to 9. So we do include 9. So in this case the description works out with set notation. If I wanted to express this in interval notation, if I went 4 is less than, x is less than or equal to 9, that's not quite interval notation. You know, we're kind of doing something like that. But remember, interval notation is when we have a low value of 4 and then the high value of 9. And then I'd be like, oh, there we go, that works. But then I realized that inside this set is the value of like 5.2 or 7.938. And this includes a whole bunch of values that are not integers. So we cannot use interval notation on this. If I wanted to get super tricky and use this aspect of the set notation, what I could do is say all x such that 4 is less than x is less than or equal to 9, and x is a element of the integer set. So that would, that's kind of a z there, that would limit it so that it only includes 5, 6, 7, 8, 9. But this is getting into kind of a very mathematical sense. So let's stick with this clean and clear one for simple sets like that. Okay, very briefly, the difference between and or in math. And would be when you're saying something is both this feature and that feature. For example, the value n is both greater than 30 and less than 50. And an and statement is going to create a single interval, whereas a or statement would create two different intervals. The value m is either less than or equal to 8, or it's greater than 4. So a or statement will create two sets, and an and statement creates one set. And one final piece is you should always list from smallest to largest. So in in this case, if you wrote the set from 50 to 30, that would be very wrong. Very, very wrong. I won't accept it at all for any points. Even though you had the correct values in there and you used parentheses, we do not count from 50 to 30. We count in the other direction. So this is wrong, wrong, wrong. All right, for examples 5, 6, and 7, I'm going to walk through the problems largely just doing them on camera, and you can copy the notes down. I'm going to speed up the instruction for these ones, though, because I think we've hit on the key aspects of interval and set notation. All right, example 5a, we want the set of n that are less than 2 or greater than or equal to 6. So in this case it's an or statement, so n is less than 2 or, actually let's go ahead and use the math symbol for or n is greater than or equal to 6. There we go. Writing this in interval notation, less than 2 would be from negative infinity to 2, and greater than or equal to 6 would be include the 6 going to infinity. The set of all numbers from negative 4 inclusive to negative 10 inclusive. This time I'm going to start with interval notation, negative 10 to negative 4. Then I check and it says inclusive, so I know I want these to be hard brackets because I'm including. And if I wanted to translate this up to set, that's the set of all x such that negative 10 is less than or equal to x is less than or equal to negative 4. And double check everything, lower value on left, higher value on right. Alligator opens its mouth to the right, lower value on left, higher value on right. Even though 4 seems smaller than 10, you have to remember that 4 is further right on the number line. All right, example 6. Express the following number lines in both set and interval notation. So first let's do this as I like interval notation, so I'm going to start both of these with interval notation. We have the interval from negative 3 to negative 2, not including, or negative 2 to 0, including, or 1 to infinity. And remember, infinities always get soft parentheses. If I wanted to write this in set, I would say the set of all x such that negative 3 is less than or equal to x is less than negative 2, or negative 2 is less than x is less than or equal to 0, or x is greater than 1. So that's pretty lengthy. All right, over to B. What we have is intervals, negative infinity to negative 4, including the negative 4, in union or negative 3, including to negative 2, excluding, or, and we got this negative 1 here, and it doesn't really cover anything. Could I do from negative 1 to negative 1? That seems kind of weird, doesn't it? So that might be a point where you say, hey, interval notation doesn't work so hot right here. So I think I'd prefer writing it in set notation. Let's finish this out. Or 0 excluding to 2 including. If you were to write it in set notation, which I think is probably better on this one, we'd have all x such that negative 4 is greater than x, so that's going to be your first interval, or negative 3 is less than or equal to, oops, I should have an equal there. Negative 3 is less than or equal to x is less than negative 2, or x equals negative 1, or 0 is less than x is less than or equal to 2, and then we close the brace. There we go. Ooh, those were some long ones. Okay, finally, the application of these. Now that we've become masters of interval and set notation, let's see how it might show up in a problem. Example 7. Sketch the following function, then find the domain. So we might remember that the square root of x looks something kind of like this. And when we look at this for domain, we have x values only from 0 to infinity. So our domain is all x such that x is greater than or equal to 0. If we wrote that in interval notation, we're talking from 0 to infinity. Another way we could have figured that out without sketching the graph is remembering that you can only take the even root of a positive number, or 0 number. So we knew that x had to be greater than or equal to 0. If we apply that to part B, we would say, oh, I know that 6 minus 5x has to be greater than or equal to 0. And solving that equation or inequality out, I get 6 is greater than or equal to 5x. 6 over 5 is greater than or equal to x. So in this case, our domain is going to be all x such that x is less than or equal to 6/5. Expressing that in set or interval notation, we would have from negative infinity to 6/5, and we include the 6/5, but not the infinity. And finally, part C, 1 over x, some people might recall, looks something like this. A graphing screen, a grapher can help you do that. We'll get into drawing these equations more further down the line. But in this case, talking about domain, we're not allowed to divide by x or divide by 0, or else the universe collapses. So in this case, our domain is all x such that x doesn't equal 0. And if you were to write that in interval notation, you'd go from negative infinity to 0 or 0 to infinity. And in this case, I prefer the set notation. Okay, I'm going to do example number 8 off camera. I will show the solution so you can check your work, but I encourage you try to work through problem number or example 8 on your own and then check it against the video. So pause the video here, work through it, and then check back. Okay, for each one of these I sketched the graph. I sketched the basic graph, and then after I had a sketch of the graph, I focused only on the portion where the constraint was true. And using a little bit of algebra, I was able to solve the inequality. You can factor this. The B and C are really easier to do if you understand how to graph parabolas, which we should have retained from Algebra 2. And then I wrote out the solutions. First I had set builder notation, and then I had interval notation. So there you have it. That's the notation that we're going to be using most frequently in the class. Interval notation, and then sometimes set notation. I'm going to save the properties of exponents for the next video, so I'll stop here. So just chill till the next episode.